Hello, my name is Ayzaan Wahid, and I'll be presenting Learning Object Condition Exploration using Distributed Soft Actor Critic. This work was done with colleagues at Robotics at Google and Stanford University. We look at the problem of visual navigation, where a robot must take in visual inputs and navigate to a location in an environment. Learning-based policies have shown promising results for navigation. Prior work, however, has generally looked at recognition, exploration, or robot control components separately. In our work, we aim to learn both exploration and control by learning to navigate to a specified object, while also precisely controlling the robot to avoid obstacles. We aim to use realistic sensors and continuous control to learn natural exploration behaviors. We study the problem of object navigation, where a robot must navigate to an object in an unseen environment. We use GibsonEnv as a set of scans of homes to provide realistic, complex visuals. We also use a realistic differential drive robot model, where a policy must output linear and angular velocity commands rather than discrete high-level actions. Finally, we emphasize the use of semantics, where we choose one of 9 object types to navigate to. The robot does not receive any other info about the goal, so it must explore the environment until it finds the object. With this problem, we bring together object-conditioned exploration and low-level control, a step towards better real-world performance compared to prior methods. To learn a policy, we train an agent from experience using reinforcement learning. We use a generic Soft Actor Critic, or SAC, algorithm to learn actions from raw observations. We use a reward formulation that doesn't provide any explicit supervision for smart or efficient exploration behaviors. We use a convolutional neural network to process visual input, with an LSTM to provide the policy with some form of memory. The policy outputs a linear and angular velocity to control the robot. To scale our setup, we create a distributed version of SAC by parallelizing the data collection with 100 CPU workers and learning using an 8 GPU setup. Using this setup, we can train 98 million experience steps per 8 GPUs per day. We train for 2.5 days, using 250 million experience steps. Using this setup, we are able to learn several emergent behaviors for exploration and navigation. In this example, we show that the robot learns a peeking behavior, where the robot enters a room just enough to check if the object is present. The robot, starting from a bedroom, traverses a hallway, peeks into 2 other bedrooms, until it finally peeks into the kitchen and heads straight towards the oven. Another learned behavior that emerges is circling, where the robot spins to capture the full view of a room. In this example, the robot must find a sofa. The robot starts in a dining room and circles around to see if a sofa is present. When it does not find the sofa, the robot exits the room to explore other areas of the house. Another learned behavior is beelining, where the robot moves straight towards the object once it's seen. In this example, we see the robot looking for a toilet, traversing a room and hallway. Once the robot detects a toilet, it heads straight towards it. We report our results using success rate and success weighted by path length, or SPL. To put our results into context, we compare to a human baseline where 12 human raters are asked to use their keyboards to navigate and find objects. Human raters are not perfect object navigators, succeeding 86% of the time, with an SPL of 0.8. Humans must perform some exploration and may not take the most efficient path. This can be seen as an upper limit of performance, and our policy approaches over 70% of human performance levels. We also find that scripted explorations are lacking. We test both the Roomba policy, which moves straight until it's near an obstacle, then turns in a random direction, and a topological graph traversal, which performs a depth-first search of a graph of the environment. Our policy outperforms both of these scripted baselines. We also find that choosing observation modalities is important in learning this joint exploration and control problem. For the robot control portion, we find that adding a LiDAR scan at the base of the robot fixes the blind spot that is present when using RGB and depth images alone, helping the robot avoid collisions in crowded environments. In addition, we use a detection image to focus on the exploration part of the problem. However, we still report results on different combinations of modalities. Thank you.